determine the rate law from initial rate data, be able to the order of the reaction with respect to each reactant, the overall order, the rate constant with units. All right, so I gave you this rate law. The next example problem is how we determine rate laws experimentally. One of the ways. This is called the method of initial rates. All right, here, method of initial rates. That's not the only way of doing it. It is one way to do it. And you are going to use this method to determine the order of one of your reactants in 2 weeks. Right? When you go into the lab, you will change the concentration of something, see how that affects the rate. Right? And that's what we do here. Right? So if we look at this, so I'm going to illustrate the method of initial rates by doing an example here. All right, so we've got iodate reacting with sulfite to form iodide and sulfate. So we've got the 3 different experiments. We mixed together some iodate and some sulfite and measured the initial rate. Right? So we somehow, there are different ways of measuring what the rate is when you put these things together. All right, here, is that what the rate is equal to? Is the rate equal to di dt? Is that the rate of the reaction, or do we have to do something to that in order to make it the rate of the reaction?
We need to do something.
Okay, what do we need to do?
Oh, no, yeah, I guess it would be.
Well, no, those are the right units. Rates are in moles per liter per second.
Add them together and divide by 3.
Nope, because those are different conditions, and the initial rate's different for. Now, the point I was trying to make is we have to look at the particular species and determine whether there's a coefficient in front of it. Because if there had been a 3 in front of that, I would have had to take this and do what? Divide it by 3 to get the rate of the reaction. Right. Mr. Baker, put your computer down. And you too. Right, you too. In my class, I want you listening to me, not looking at your computer. Yeah, Mr. Fish, you do it too. Ah, there we go. Mr. Rudy. So, Ms. Cox. All right. Everybody, pay attention to me. Don't be, surfing the. I still got 2 right in front of me.
Look, this is not fun.
If they're off, then I guess that's not a problem. But I have no way of telling that. So, all right. So anyway, this is the method of initial rates. If there had been a 3 in front of this, I would have had to take these numbers right there and do what? Divide by 3 in order to get the rate of the reaction. This is the rate of how iodide is changing. And depending upon what the chemical reaction is, it either may be the rate if there's a 1 and it's a product, or if it's if this had said iodate, then these numbers would all be negative, and I would have had to change them to positives. If this had been in terms of sulfate, I would have had to divide that by 3 because of that 3 rate. All right, so but for now, in this problem, that does represent the rate because that is equal to the rate. All right, so the way to approach these problems is to try and find where one of the reactants changes while none of the others do change. Right? So you isolate one that changes. In this case, we only have 2 reactants. Here's what the sulfite does not change, and the iodate does. Right? So we're going to look at these 2 experiments, and by doubling the iodate, we're going to see how that affects the rate. Anybody tell what that did? It doubled the rate. So what does that mean?
Second order?
Nope. It would mean it's first order. But let's look at that. All right. So for experiment 2, the rate is equal to K times the concentration of 0.2 to the x power and 0.1 to the y power for that. So that's 2. The rate for experiment 1 is K times the concentration 0.1 to the x power and 0.1 to the y power. Okay, can we all agree on that? So far, so good? All I've done is take those concentrations and put them into the rate law. Okay, and we know the rate here is equal to 0.0512, and this one is equal to 0.256. All right, now I'm going to divide both sides by the other, right? This is an equality, so I can simply take this divided by this. That's still going to be equal to this divided by that, right? So if you have 2 equals 2, and you have 4 equals 4, and you divide 2 by 4 on this side and divide 2 by 4 on that side, then it's going to give you the same answer. Still going to be an equality. All right, mathematics. All right, so does anything cancel there then?
Yes.
Yes?
Why'd you put experiment 2 on top? Is that just because it's 3?
Yeah, because I want that to be a whole number. Yeah, if you wanted to do the other way, you could. You'd get 1/2, and you know, I just knew ahead of time what. But we could have done 1 first and do the second one. Anything cancel here?
Okay.
K cancels. Very good. The 0.1 to the y power is exactly the same thing, regardless of what y is, since it's the exact same thing. But that doesn't cancel, although this then becomes, all right, so the ratio here is equal to 2. And actually it's good to 3 significant digits. And this is equal to 2.00 raised to the x power. All right? If you take this, 0.2 to the x power divided by 0.1 to the x power, that's equal to 2 to the x power. Okay? And so therefore, x is equal to 2 equals 2 to the x is equal to 1. Okay, so what would we do to get what the value of y is? What's the matter?
Choose 2 different equations or experiments that have the same, like the iodide.
Yeah, which ones? Which ones have the same iodate? Which ones would I choose here?
1 and 3.
1 and 3. So now I'm going to take those 2. Okay, and I'm going to do the same thing here. Now, I'm going to do the abbreviation here. We've just seen how the one that has the same concentration, the rate constant, gets canceled out when we do this. So I'm just going to say, all right, between here we've got the concentration, this to this is equal to 2. All right, so that's 2 to the what? This divided by that is 2 to the y. I really should have said, all right, this is equal to k times the iodate, the x power, and the sulfite, the y power, right? So now the iodate's staying the same, so that will have no effect on the rate, and it's only the sulfite that is changing, right? So, and that has the exponent of y. So the ratio here is 0.2 to 0.1, so that becomes 2 to the y is equal to the ratio of this, which is 0.102 divided by 0.0256, right? And that is equal to 4. All right, so therefore, the value of y is equal to what?
2.
Is equal to 2. Okay? So, there's one other part of this that we have to finish, right? We've got the exponents, the orders of the reactions, but we also have to determine the value of the rate constant. So how do we determine the value of the rate constant? K is going to be equal to, so now we know that, based on experiment, that that's equal to 1, and that one's equal to 2. So K is going to be equal to the rate divided by the iodate to the first power and the sulfite to the second power. So what do I put for the rate?
Whichever experiment you choose.
Yeah, just choose one of those experiments. Let's take the last one. 0.102. I could have taken either of the other two. I just happened to pick this one. So that's 0.102 molar per second divided by, let's see, the concentration there is 0.1 molar to the first power and 0.2 molar squared. And then that's going to give me my value for my rate constant. And of course, we have to come up with the proper units on that. Okay, and I get, is that right, 25.5? Anybody check that out? And it's good to three significant, all of our numbers are good to three significant figures there. And so what are the units on that rate constant?
Molar to the -2, second to the -1.
That is correct. Okay, that's called the method of initial rates. And it's a very useful way for chemists to determine orders of reactions. And so once you have the rate law, then you can then determine what the rate will be under any circumstance. Now, if this were a real experiment, then what I would do is determine what the K was for all three of those experiments. And then what would I do? I would take the average, right? Because in real experiments, you don't get the exact same number every time. Now, this is not a real experiment. I just made this up and made it so you get the same K value every time. But in real experiments, there will be experimental error, and so you might get a K of 0.1, then one that's 0.12, then one that's 0.085 or something, and you take those three and average them. Theoretically, they should all be the same, but because of experimental error, they will normally be slightly different. And then so you take the average. All right, so on the next page, backside, there is another method of initial rates problem. All right, so you guys can try and help me get this one. Let me just say this. This method is a learning objective, and it's very important for you to be able to do these kind of problems, because I guarantee you'll see one on a quiz, and you'll also probably see one on the 6-week exam. I cannot remember the last time we've had a 6-week exam where we didn't have a method of initial rates type problem when we've covered kinetics, right? So this is considered important, and you'll probably see something like this on the final exam too. So you need to be able to work these kind of problems. All right, so here we've got three different reactants. All right, so my generic rate law is going to be what? A to the x power, B to the y power, and C to the z power with a rate constant K in there. Gotta have the K. Now, is this the rate of the reaction? Here it says dd dt. Is that the actual rate?
No.
No. So, what is the actual rate?
Divide by 2.
Yes, we'd have to take each of these and divide by 2 to get what the rate is. All right, so here we're given how d is changing. Since there's a 2 in front of the d instead of a 1, then since we're given this, we'd have to divide that by 2 to get the rate. Which won't be important in determining the value of x, y, and z. Right? If you don't do that and solve for x, y, and z, no problem. You'll still get the same answer. However, when you go to calculate the rate constant k, then you'll get the wrong answer for the k. Right? So you have to keep in mind you have to have the rate in order to properly solve for the value of k. All right, so let's try and get what a is. All right, what experiments will we use to try and get a? We got 4 experiments. 1, 2, 3, 4. Which experiments will we use to get what a, the exponent on a is?
1 and 2.
I think it's 1 and 2, isn't it? Here that changes, that doesn't change, that doesn't change. Right? So B and C don't change, and A does. So we've isolated A. So I'm going to take 2 divided by 1. So when I take the second experiment divided by the first experiment, what's the ratio of the concentrations? 2. And that's going to be 2 to the x power is equal to the ratio of, so that's 0.707 divided by 2, divided 0.0707. 0.707 divided by 0.0500 divided by 2. So you see that the 2's don't matter in this case, right? Those just cancel. What is that ratio right there? 1.4.
1.4.
Okay, it's only good to 3. So 1.141. Okay. Wow. That x is not necessarily easy to figure out. Anybody know what x is here?
1/2.
Okay. The way you would do that if you don't see that, so the square root of 2 is in fact equal to 1.4, right? So that's correct. But let's say you didn't see that. How would you mathematically solve for x? Take the log of both sides. So if I take the log of that side, what do I get? X log of 2 is equal to the log of 1.41, right? And then I would take and divide by log of 2. And when you do that, what do we get? So the log of 1.41 divided by, oops, I want to then divide by the log of 2. Then I get the value 0.496. Okay? So, oops, I was wrong. It's not 1/2, right? It's actually 0.496. Should I use x equal to 0.496? Okay. No, I don't. I say that ratio would be, what, 496 divided by 500, which then is, what, 249 divided by 250. Does that sound like a reasonable small whole number ratio? No. You want small number ratios, that's fine, like 1 to 2, but not 496 to 500. That doesn't make any sense. So we'd round that to 1/2. All right, now I want to get what b is. What experiments would I look for to get b? 2 and 3. All right. Here, a stays the same, and c stays the same, and b is changing. Okay? So, the ratio, and then I'm going to do 3 to 2, since the concentration is bigger. I want numbers greater than 1 on these things. We wouldn't have to do that, but that's just the way I like to do it. So what the ratio of the concentration is 4. So that the ratio of the concentrations raised to y is equal to the ratio of 0.2828 divided by 2 divided by 0.0707 divided by 2. 2's cancel. Does that look like it's equal to 4? Yeah. Okay. So 4 to the y power is equal to 4. Therefore, y is equal to 1. We're getting closer. Now we need to get z. So what experiments do we have where c is changing but a and b are not? I think it's 1 and 4, right? Yeah, so 0.1 to 0.1, 0.1, 0.1, and 0.3, 0.1. All right, so now we're going to look at these two to get what c is, right? So, or what the exponent on c is. So here I've got a ratio of 0.3 to 0.1, which is 3, raised to the z power is equal to 0.4500 divided by 2 divided by 0.0500 divided by 2, and that is equal to 9. So therefore, z is equal to 2. Okay? So now our rate law in general is equal to k times a to the 1/2 power, b to the first power, and c squared. But we need to now solve for k. So how do I get the value of the rate constant k? It would be the rate divided by a to the 1/2 power, b to the first power, and c squared. So that's going to be equal to which rate? Doesn't matter. I'll just arbitrarily pick the first one. This is where it matters about the 2. Right? If I don't put the 2 in there, then my k is going to be wrong. Right? So that's moles per liter per second. And the value of a is 0.1. to the 1/2. Yeah, they're all 0.1 molar.
B is 1 molar.
0.1 molar. Okay. And so I got to make sure I divide by that 0.05 by 2 in the rate, or else my number is going to be too big.
So your numbers messed up.
Pardon me?
Your numbers.
Which number do I have messed up?
B equals to 1 molar and C equals to 0.01. You got
Wait a
all-
minute. B
Oh, my bad. I'm tripping.
is equal to 0.1.
I'm tripping. My bad.
Okay. I know I'm wrong periodically, but I don't think that this time. I think I got it right there. That should be 0.5 divided by 1 cube. All right, so I got on my calculator 79.0569415. How many digits am I justified in having here? 3. So 79.1. And I have to have the right units, or else I get points taken off. Yes.
So for C, why did you use 1 and 4 instead of any of the other ones? Like
Because you have to find where C changes, but the others don't. Right? If the others change, then the rate is being affected by that other one too. So 1 and 4, I'm using so I'm 1 and 4. C changes, right?
Yes. Okay.
Okay.
I understand.
And B doesn't change, and A doesn't change.
Thank you.
You're welcome. All right, so that will be molarity to the something, seconds to the -1. So what is the molarity to? Nope. I think that is 7/2 for the so that would be to the -5/2, right? 1 minus 7/2 minus 5/2. Okay. Anybody have any questions on what we covered today? All right, so we've covered all of those learning objectives. I do want to do just briefly one thing before we go. All right, so here's some data for a chemical reaction. Let's say A goes to form B. Okay. If I want to figure out what the average rate is between 50 and 150, how would I figure that out? The average rate between 50 and 150. So the rate of this reaction, there's a 1 there, so if the rate is equal to minus the change in A divided by the change in time. So what would I put for the change in A? 0.0783 molar minus 0.0894 molar divided by 150 minus 50 seconds. Okay, that's how I would calculate the average rate given that. Okay, let's compare that to what the rate is at 50 seconds, the instantaneous rate. Right, so 0.0783 minus 0.0894 divided by 100. Okay, so that's 1.11 times 10 to the minus 4. Right, and you probably want to check with that. 1.11 times 10 to the minus 4 molar per second. Hopefully I did that right. Okay, what's the instantaneous rate right there? How would I figure that out? Right, so I've got a plot, I can kind of connect these things. And which one would you expect to be greater in terms of the rate? The one here or the one from there to there? The instantaneous rate right there should be greater, right? The average rate we just calculated is the slope right there. That value right there. That's what we just calculated between those 2 points. All right, and so the instantaneous rate I would calculate by doing a tangent line here. Now, I guess the question is, how good am I going to make a tangent line? But we'll get an estimate of what the instantaneous rate is from that. So minus dA dt is equal to the instantaneous rate. So that would be, all right, what value is that? That like 0.098, and that's 0.06, so that would be the 0.098 minus 0.06, and that goes from, what, maybe 230, 0 to 230, all right? And so that will give us what the slope of that line is, and that's how you could get, from a plot like that, that's how you get the instantaneous rate, is by draw a tangent line and then figure out what the slope of that is. And that better be bigger than what we just calculated, I hope.
Professor, could you move that view down, please?
Oh, down. All right, so yes, I'm not going to be able to get the whole thing on. All right, so, man, that's hard to see. All right, so anyway, I guess y'all just have to look online at this if you can't see that very well. So anyway, that's, I'm getting the instantaneous rate here of 1.6, at best, 1.7 times 10 to the minus 4 molar per second. So now this tangent line is approximately what the instantaneous rate would be, at the midpoint, 100 seconds. So here's 1.7 times 10 to the minus 4th. If we go 50 seconds later, the rate is 1.1 times 10 to the minus 4th. So what's happening to the rate as the reaction proceeds? It's getting smaller, right? It's decreasing until what's the rate at the end of the reaction? 0. All right. Time to take the quiz. So put away all your stuff that shouldn't be on your desk. And we will take the quiz.
Yeah, sure.